In the next two videos, I'll present numerical measures of center and spread. In this video, I'll focus on measures of center, namely mean and median. Let's start with a review of the definitions of these measures. When we talk about an average, we're often referring to the mean. To compute the mean of a data set, we add all the values for a given variable and divide by the total number of values. I've written this symbolically, where x bar is the common symbol for a mean. The sigma represents taking a sum, x stands for the values of the variable, and n is the total number of data points. Whereas the mean is an average, a median measures the midpoints of values. To calculate the median, put the values in order from smallest to largest. Then the median is the middle value on the list. Let's work through these calculations on the bird count data we looked at in the previous 5.1 videos. For the mean, there were 21 data values. So we add up all the values in the table and divide by 21. The mean comes out to be 172.9. For the median, I first put the data values in order from smallest to largest. Since there are 21 values in total, the middle value will be the 11th value on the list. This ends up being 166. In what ways can we conceptualize these as measures of center? One way to think about the mean is as a balance point for the frequency distribution. For data with a single typical value and a symmetric distribution, this balance point will fall exactly where we would expect the center of the distribution to be, and thus the mean is a good measure of center. However, for skewed data or data with outliers, the mean will be a less effective measure of center. This is because the distant values will have a larger impact on this imaginary balancing point. For example, the histogram shows a single earthquake with magnitude 3.6. This point, because it is far from the balancing point, has an outsized effect on the mean, making the mean smaller. We can also visualize the median on a distribution. Recall that the median is the midpoint of the data when ordered. Therefore, on a histogram, the median will correspond to the point that divides the area of the histogram in half. Note that the median is less susceptible to outliers and skewness in the data. For example, consider again the earthquake with a magnitude of 3.6. If this value was moved up a bit or down a bit, it would have no effect on the median, since 50% of the data values would still be below 7.0. The bird count data illustrates the effects of skewness on the mean. The data is skewed left, pulling the mean to a higher value than the median. Note that the median better aligns with the visual center of this data. For symmetric data, the mean and median generally align, and the mean is often used. However, for skewed data or data with outliers, we can see in this example that the mean and median can differ significantly. This sometimes leads to misinterpretation or miscommunication. Taxes are one example where this has happened. In the mid-2000s, President Bush enacted several tax cuts, which were later renewed by President Obama. Here's a quote from factcheck.org discussing measures of center for these tax cuts. President Bush stumbled February 19th, saying the average tax cut is $1,089. The White House corrected that figure to $1,586. But the fact is that most Americans won't see anywhere near either of those amounts. As we said before when disputing equally misleading lowball figures given by Howard Dean, half of all individuals and families will get less than $470, and half will get more. The average is misleading because it is inflated by very large cuts given to a relatively few at the top. Here, the 1598 figure is referring to the mean, whereas the 470 figure is referring to the median. Why are these numbers so different? Incomes in the U.S. are highly skewed to the right, meaning that most incomes are clustered around low values, with increasingly fewer values spread out over higher and higher income intervals. This skewness pulls the mean higher than the median. Here's another example. The histogram shows the expected lifespan for U.S. females born in 2012. For example, the prediction is that slightly less than 1,000 out of 100,000 women will live to the age of 100. Looking at the entire histogram, we can see that the data is clustered around 85 to 90, the typical value, with a majority of lifespans between around 70 and 100. The graph is highly skewed to the left, showing that most are expected to live to old age, but there are a small number of deaths at younger ages as well. What effect does this have on measures of center? The figure normally reported as life expectancy is in fact the mean of this data. Here, the mean is 83. The median is 90. Looking at the histogram, the median appears to be a better measure of center for this data, while the mean is pulled down by the left skewness.